Hello everybody and welcome to another E5 podcast. My name is Paul Meenan and I'm going to be flying solo again tonight. Tonight, or maybe this morning or this afternoon, depending on where and what time you're listening to this podcast, we're going to be talking thought piece. We're going to be talking about really complex devices, commonly known as residual current devices. So, first bit of interesting fact, the term RCD doesn't actually exist. And when you actually look into RCDs, all you'll see is the term RCD is a parent type overview name for a suite of devices manufactured to various BS and BSEN standards. So, for instance, the residual circuit current breaker, which is known as RCCB, which is manufactured to BS 4293, which is the old school way, or the new school, which is BSEN 61008, and that is literally a device that just monitors earth leakage. Now, what's the difference between a 4293 and a 61008? Well, very simply, at the tripping time for the I delta N at one time for a 4293 is 200 milliseconds, and 40 milliseconds at 5 times, and for a BSEN 61008, at 1 times I delta N, which is the rated residual current value, it's 300 milliseconds. So there's 100 milliseconds difference between the old, which were very much all heavy, clunky, magnetic type devices, and the new, which is the more electronic devices. If you add into an RCD, MCB, which is basically overload protection, or for what we commonly known as the magnetic and thermal properties of an MCB, it becomes something called a residual current breaker with overload. That's manufactured to a standard BSEN 61009, and that's really where most of us are heading at the moment within our electrical installation careers, putting in single module RCBOs to ensure that we don't get nuisance tripping. We're dealing with protective conductor currents and all the other bits and bobs. But what other types of really complex devices are there? Well, you have something called an SRCD, which is a socket outlet incorporating an RCD, which is made to a British standard 7288, which aligns with BS 4293 for the tripping time. You then have FCU RCD, which is a fuse spur of an RCD, again to BS 7288, so it's a 200 milliseconds trip time. So the field device, straight away, it trips more stringently than the board, consumer unit side. And then there's something called a PRCD, which is a portable RCD plug. So that's the one that you plug your lawnmower in if you're in a really old house. It's a portable RCD, basically built into a plug top. That's manufactured to standard BS 7071, which is still current, is still valid, although it has not been updated since the early 90s. So yeah, so there you go. So that's just some of the other really complex devices. You've got a bit of a suite or a family, henceforth the term RCD. So if we step forward in time and go to the current edition of BS 7671, which is the 18th edition, 2018, there is a regulation number 5313.3, and it's called Types of RCD. Now, hallelujah, because I've been saying this for years. Now, for those who know me know I work in rail, and in rail you get a lot of weird electromagnetic problems. As we know, electrical installations, you could break them down to 3 fundamental characteristics, which would be electromagnetic, thermal and chemical from a reactions perspective. And within the current edition, they finally released Regulation 53133, and it states different types of RCDs exist. Hooray! First ever acknowledgement. Depending on their behaviour in the presence of DC components and frequencies, the appropriate RCD shall be selected from the following. And then it says, item 1, RCD type A, which is an RCD trip-in on alternative sinusoidal residual current, suddenly applied or smoothly increasing, i.e. gradual leakage or a quick release. Then there's RCD type A, which is RCD tripping on alternating sinusoidal residual current and on residual pulsating direct current, suddenly applied or smoothly. So that's an RCD that will still provide earth leakage detection even when there is a pulsating DC. DC in electrical installations. You might want to check out the E5 group channel for a video on what it actually does to AC RCDs, but there's a term remnants, there's a term blinding, shock, stun, saturate. These are all different terms that are used for when DC gets into the electronic components or the magnetic components of an RCD. So it also mentions type F, for which tripping is achieved as for type A, and in addition for composite residual currents, whether applied suddenly or slowly rising. So two different types of DC here. It's really becoming more finite. Slow leakage of DC with a rise, or a sudden leakage of DC. Now that's intended for the circuit supplied between line and neutral or line and earth. Now it also says for pulsating direct current superimposed on smooth direct current. So DC, positive and negative. Now there are two types. There is always a pulsating, which is one where AC is chopped and broken down into the DC, which you're never going to get a smooth line. But then there is also, if you have a battery system which produces DC, you will get smooth direct current because it's not being converted from AC, it's just coming naturally from the chemical reaction in a battery producing electron flow and giving you a smooth DC. So electrical installations nowadays, we're looking at battery storage. We're looking at a lot of new technology, lots of emergency battery packs already in installations, UPSs, Tesla walls, solar roofs, battery storage in your car. When your car is charging, your EV car, that then almost becomes a battery storage, energy storage unit for your house. This is where electrical installation is heading. So you need to be prepared to experience lots of different types of DC. LED lighting. The drivers can produce DC current leakage in their normal or fault operations. If we look at USB sockets, which we've done a video on, we can also produce leakage there where there's a dielectric breakdown within the rectifier or the actual fundamental insulation of the back of the socket from the energy it produces. There's also a note, and it says for type F, tripping is achieved for residual pulsating direct current superimposed on a smooth direct current up to 10 milliamp. So here's the problem. We can't anything more than 10 milliamps, and you're basically in a lot of trouble. You're going to have to then go specialist, bespoke equipment. You're then looking at a company called Blakely. Blakely do massive industrial, heavy-duty, really good quality switchgear, site distribution cabinets, and their stuff goes up to 0.5 amp from last memory served. So that provides immunity for up to 0.5 amp. But again, their stuff is based on the old BS4293 standard, and they work from the standard. They've developed specific technology to mitigate the presence of DC. So there's a note 4, and it basically says RCD type B, RCD for which tripping is achieved as for the type F, and in addition for residual sinusoidal alternating currents up to 1 kHz, for residual alternating currents superimposed on a smooth direct current, and for residual direct currents superimposed on a smooth direct current. So basically type B is it will, no matter what your scenario, if there's AC or DC in the same circuit, it should be able to protect as long as the frequency on that circuit or harmonic interference or connected load doesn't go above 1 kHz, and also that there's no more than 10 milliamps. So they're the types you get now. Okay, but that's just according to BS7671. But there is more, and this is where it gets a bit weird, really. So there's lots and lots of technical reports published by the International Electrotechnical Committee, one of them being 62350, which is guidance for correct use of RCDs for households and similar use. And lo and behold, most of you are going, I have never heard of that. Why is that not being referenced anywhere at any time? And that does actually cover the Type B, because Type B also covers residual pulsating direct current, which results from two or more phases. For residual smooth direct currents, whether applied slowly or increased, and it doesn't matter about what the polarity is from the DC perspective. There's also notes that state for Type B, tripping is achieved for residual pulsating direct currents superimposed on a smooth direct current up to 0.5 times the rated residual current, or 10 milliamp. So they stop at 10 milliamp, which is worrying. It's very worrying. Let's be honest about it. And nobody really likes hearing that sort of thing. It then also says for general purposes, Type AC may be used. What is general purpose nowadays? Well, immersion heater, standard lamps, maybe supply to a shed. But then again, if somebody's got a VSD or some sort of DC generating equipment, it's not really going to be very good. The general purposes is kind of a cop-out, really. So next bombshell for you is AC RCDs have been banned in many parts of Europe. If you do any temporary events or temporary generation stuff, BS 7909 bans the use of AC. It doesn't recommend it. EV chargers now stay Type A. In the recent podcast we did with John Ward looking at Amendment 1, the proposal, that states a Type F, which is quite interesting, because that effectively acknowledges that there could be a back frequency or some sort of frequencies appearing on electrical installations from EVs, which is never really that good a thing, if you ask my view. Now, the wonderful people on YouTube, Dave Watts, has done a great video where he said, do we still need to have Type AC RCDs? I have been crusading with the E5 guys for many years over RCDs. I am a firm believer in the fundamental principles of good selection and erection, mechanical protection, and ensuring all external influences and access is prohibited from unauthorised persons. So I'm a firm believer that RCDs there are lots of places where they shouldn't be applied. John Ward, I think, is of the same view as are many of the E5 members. However, if you look at the electricity at work regulations, you have to take all reasonable steps to prevent the commissioning of an offence. That commissioning of an offence could be not selecting the right electrical equipment. Regulation 5 comes to mind straight away. So we have to pick RCDs, but it's how we pick them and making sure we're taking all reasonable steps to avoid the commission of offence. Now, this is where it gets really confusing, because the standards, God love them, are really, really contradictory. So the definition of residual current in 7671 is the algebraic sum of currents in the live conductors of a circuit at a point in the electrical installation. That's the definition of residual current, which is on page 36. Most of us go, pardon? What? The algebraic sum of currents in the live conductors. Remember, the live and neutral are conductors. And when you do earth leakage tests, you'll put your clamp around the live and neutral, and that should give you a good indicator of what's going in and what's coming out. Now, if you look at BSEN 61009, the standard for residual current breakers with overload, that says residual current is the vector sum of the instantaneous values of the current flowing in the main circuit of the RCBO. Page 14, section 323. Good God, okay, so they are kind of similar, but not. Then there's a term called protective conduct current, which we should all know because it's been in 7671 for a while. Some people have wired up circuits and gone, oh, I need a 10 mil because I've got quite a lot of earth leakage coming from my stuff. So protective conduct current, though, is electric current appearing in a protective conductor, or CPC, such as leakage current or electric current resulting from an insulation fault. So protective conductor current is resulting from an installation fault, and that's page 34 of 7671. However, the term leakage current, which is different from protective conductor current, is the current flowing from the live parts of an installation to earth in the absence of an installation fault, and that's critical. So leakage current is basically defined as the normal operation of an electrical installation where current flows from live parts. Now that could be an earth printed circuit board where there's static which can build up and may just need to discharge down to earth. but that then produces leakage current. Protective conductor current is only when there is an insulation fault. I think a lot of people we get them mixed up, and the reason being is leakage current is defined in section 3.1.2 of 61009, and protective conductor currents in it's chapter 2 of 7671, page 34. So there's a little bit of a difference in those two terms. Now, I'm not going to go through how an RCD works, but effectively it's monitoring of the line and neutral conductors, which are both live or energized conductors. And there is a winding around a solenoid or some sort of iron core, and a little coil which then goes to a relay, and a sensing coil which then effectively operates a shunt trip when there is an imbalance between the line and neutral conductors. Fundamentally how they work, basically. The water pipe analogy would work as well, where effectively water going in must be the same going out, and if there's a leak on the load side, it will detect that before the leak becomes too dangerous, and a leak of energy, i.e. no more than 30 milliamps or another value, and it will then disconnect both line conductors. That's very important. It isolates the device, and the only way of isolating is the disconnection and separation of all sources of electrical energy in such a manner that it's secure. Now, that's the definition of isolation, but it does that until you go back and try and reset it. Now, the RCD has some origins going way back to the 60s. In fact, in 1963, there was a US patent put in, and I believe Eaton, or one of their original companies, patented one in the late 50s for a trip circuit and a basic solenoid, but that actually ran the earth through the core. So yeah, technology's been there for many years. Now, a bit of history in this country: there were two types of earth leakage circuit breaker, known as ELCBs, and they were recognised by the regulations. There was a voltage operated type or a current operated type, commonly known now as our RCD family. The voltage operated type, which was just insane, had two earth references. One was a local electrode and one was basically the earth at the installation, and it would monitor the potential difference between them two. Once it went above 50 volts, it would then trip. However, as you can imagine, waiting for a voltage to go above 50 volts with no limit on the current could easily kill somebody. So not really good, which is why we now go with current operated RCDs. So RCDs are defined by three main characteristics. Their rating in amps. Okay. The next one is their rated residual operating current of the protective device in amperes, which is known as the I delta N. Now, you can get RCDs now in 10 milliamp, 30 milliamp, 100 milliamp, 300 milliamp, 500 milliamp, and on the big commercial industrial stuff, you can get these little VIGI units which allow you to vary from instantaneous trip or time delay, which permits selectivity, which was formerly known as discrimination, and they're called S-types or special, selective, more on the big stuff. But if you've got two RCDs in series, you do need to ensure selectivity or discrimination between the two. So yeah, that's the kind of three characteristics really: the rating in amps, the residual current, and when the instantaneous trip occurs, whether it's intentional or time delayed and special. So what types of RCDs are out there? Well, there's an AC, and an AC ensures tripping for AC currents, whether sudden or rising. That's what we've been using the last 20 plus years. The A-type is a squiggly line with some what looks like railway arches, and that deals with pulsating DC currents. The arches show the pulsating effect on the DC, which has been rectified. You then got one called an AKV. Now, an AKV is basically an A-type, but it also has a 3000 amp transient protection built in. So it's almost a surge protection device as well, or an immunity to 3000 amp transients which could appear. So an AKV one, not generally available in the UK, but it can be got. There is also the F-type. F-type uses the A symbol with another symbol next to it with what looks like a really fast sine wave to represent those high frequency faults up to 1 kilohertz. And that's now where EV charging is going. You've then got the B-type, which is the same symbol as an A-type, plus the F-type, plus then a box with a solid drawn line and a chopped or broken solid line. That's B. So that covers pretty much all of, up to 1 kV, 1 kilohertz, sorry, and 10 milliamp. Type B will protect. However, there is more. So there is a device called a B+, but there is no BSEN standard yet for this device, which is why it's not recognised by BS 7671. Now the B+ ensures tripping for AC currents, pulsating DC currents, and smooth DC currents, whether it's sudden or rising. But it also goes one extra and ensures no unwanted tripping and detection of high frequency faults up to 20 kilohertz. So that'll have a little box that says kilohertz on it. So type B, 1 kilohertz. Type B+, 20 kilohertz. Now I have bought these. You're looking at 500 nicker a go. At least 500 nicker a go, and to be honest with you, the Bs will probably cost you 500 nicker, but I got a good deal on some B+ stuff. They are ridiculously expensive, as you can imagine. So yeah, Siemens do B type, and they are huge. They are 4 modules wide for a single pole circuit. Just put that into context. It's huge. It's absolutely massive. There's also an EV type, which basically does like the Type A, but up to 6 milliamps, and it does up to 1 kilohertz, and is resistant to 3000 amp of transient. So EV are again, you may find some wholesaler gives you some dodgy stuff, and it's called an EV. They are around in Europe, but what do we have to consider when we're selecting a safe RCD? Well, onboard EV chargers, their design can impact on the RCD selection. So when you're doing EV, it's chapter 722, worth getting the guidance notes, worth looking into Amendment 1. The last thing you want to be doing is putting in a Type AC RCD or a Type A, and in 5 years' time, it's a minimum of Type F or B, and you're then coding C2 or C3, so you don't want that. Some EV charger characteristics can cause nuisance tripping or RCD blinding, stunning, shocking, saturating, because it's a big DC battery that's sitting outside your house. So you really need to understand the technology, which is why it's worth going and working with the manufacturers to train and understand that. So, Type A, yep, 6 milliamp DC, but again, Type F, Type EV, Type B, Type B+. And there's one thing you need to be very aware of, is if you look at the general arrangement of an electrical installation, if you have, let's say, a TT installation, you may have a Type A RCCB as a main switch, which will obviously be a special or selective because there'll be time delay. Now downstream, you may have Type A RCBOs, which is all fine and dandy. But if you then go in and put, say, a variable speed drive or something requires a Type B, or by the manufacturer's recommendation, you can't put that Type B downstream of a Type A. So what you would have to do is you would have to effectively Henley block your meter tails, put in a new subboard, and the Type B would have to go before all of your fixed installation, or at least in parallel from chopping those tails. Again, the whole selectivity perspective of it, it's got to arrive at the right location and do the right thing. So that's one thing that's worth noting on RCDs. Now this is the golden nugget, because I've been waffling for 20 odd minutes. RCDs, how do you pick them? How do you pick them? There's a regulation, and that regulation is found in section 531. More specifically, a regulation which was introduced, 53132, and it's called unwanted tripping, and it quite clearly states residual current protective devices shall be selected and erected so as to limit the risk of unwanted tripping. So this is where we always say that the whole split load boards, they're a dying thing. Split load boards they're not selected and erected to limit the risk of unwanted tripping, because we know it bloody happens when a bulb trips in a lot of houses with good earths. So it says the following shall be considered: subdivision of circuits with individual associated RCDs. And it says RCDs shall be selected and the circuits subdivided in such a way that any earth leakage likely to occur during normal operation of the connected load will not cause unwanted tripping. Now remember that normal operation is a key thing, not fault, but normal operation. So this is equipment that's electronic, that leaks in its normal operation current to the earth via the CPC. Then also says in order to avoid unwanted tripping by protective conductor currents and or earth leakage, the accumulation of such currents downstream in the RCD shall not be more than 30% of the rated residual operating current. So on a 30 milliamp device, that's what, 9 to 10 milliamp. On a 100 milliamp device, that's 30 milliamp, etc., etc. So as you can see, we need to start working this stuff out. There's some notes that says this will allow a better selection of the type of RCD, and this is the whole leveling up. This is the upskilling part here, is we need to get far better at selecting and erecting RCDs. We need to be far better at understanding the behaviours of RCDs. And it says in the case of transient effects, tripping of RCD may occur by charging of bypass capacitors or by other electromagnetic disturbances. It also says coordination of general type RCD, selective and time delay RCDs. It's got coordination of RCDs with surge protection devices, according to regulation 53447. So there's quite a lot. It then also obviously defines, as I've gone through earlier on, the different types of RCD. So section 531.3 is a real place to learn about RCDs. So I'm an electrician. I'm going to a wholesaler and I need to pick a new consumer unit, and I want to go with RCBO, but what do I do? How do I work out when I'm designing my installations? Where's the guidance on how I work out the leakage current for a domestic installation? Well, here's your golden nugget if you're still listening. International Electrotechnical Committee Technical Report 62350 actually has a formula for working it out, and I'm going to tell you now. That formula is very simple. To work out the leakage current per circuit, what you do is you work out the sum of the connected appliances and you multiply that by 0.75. That will give you the leakage current per circuit. Now, hello, what was that you just said? Let's give you an example. It actually has some appliances. A PC laptop will generate 1 to 2 milliamps of leakage current. A printer, 0.5 to 1 milliamp. Mobile devices, 0.5 to 0.75. On other appliances, could be over 3.5 milliamps. So, let's say we've got an office with, 20 computers. Yeah? So if we've got 20 computers, we've got 40 milliamps, worst case scenario. Okay? So 40 milliamps times 0.75 is 30 milliamps. So we could technically put 40 pieces of IT equipment onto one circuit and it would more than likely trip. Maybe it won't, because again it depends on when that residual current occurs, whether it's normal or fault current. However, we would never do that. Realistically, if you had 2 milliamps per laptop and you were following the no more than 9 to 10 milliamps, you would effectively be installing at least 4 to 5 circuits, which is a problem because it makes the boards bigger. However, it does reduce the need for it reduces the risk and the likelihood of nuisance tripping on the circuit. Again, this all comes down to budget, but it also comes down to good design, section 123 of 7671. You need to think about it, consider it, price for it, and come up with options. So I'm going to do a video that expands on this probably a lot more, which will go in series parts. So yeah, this is just kind of the summary really. But that's the way you work it out. Leakage current per circuit is the sum of connected appliances. So if you've got 10 or 15 or whatever, you work out using the figures in IEC 62350 and you multiply by 0.75. So you derate it. You derate that total to give you a factor of safety, and that will give you your leakage. Or you can measure, but again, you're designing. Measuring is the after. If you're maybe doing a rewire, you can measure before you do. You could look at earth leakage. You can look at a number of characteristics of the installation, maximum demand, etc. by doing load monitoring, but that's more on the commercial industrial side. So I'm going to leave it there. I think I've bored you to death with RCDs. It's a fascinating subject. They're going to get more complex. They're going to get a hell of a lot more complex. Amendment 1 is now talking about DC RCDs, which are RCDs that literally just do DC. So they're going to get more complex, more harder, and we've got a choice. We get on board and we adapt and we embrace and we learn and we grow, and our businesses and hopefully the money coming in can increase and be steady and stable. Or we can just go against the grain and just find ourselves doing basic house bashing, chucking in a load of rubbish, or just chucking in the basic stuff and then getting the work snagged and ripped to pieces. It's entirely down to the individual. So that's enough for me. Hopefully this has got you thinking, and until the next thought piece, you've been listening to Paul Meenan, and that's it. Thanks for listening.